that'll be the first one that we'll look at here today. And then what I'll do is just kind of give you guys a second to just kind of familiarize yourself with the questions, because I'm not sure if you looked at them ahead of time or not. And then just kind of give you a little background information about, you know, what is this question asking you for? And then I'll give you guys a few minutes to kind of try and solve. I'll give you, a couple little pieces at a time, and then we'll break it down in chunks, and then I'll go over those answers in chunks too. So this free response question is going to be asking you things about atomic theory and periodicity. So either about the structure of atoms themselves or about their organization on the periodic table. So why we might organize, the sulfur to the left of chlorine on the periodic table, something like that. The bonding structure itself, and then there's a little bit of a kinetics tie-in too towards the end of this problem. Okay, so if we look at this problem here, the first couple of questions there is telling us that we're looking at a structure of sulfur with 8 atoms connected. It's only showing the bonding pairs of electrons. It left out the lone pairs. So it's going to have you try and figure out how many lone pairs it is. What do you think the bond angle would be? And figure out the electron configuration of sulfur in its ground state. So I'm going to give you guys just a couple minutes to do if you want to just do parts A, B, C. Take your best guess, and then I will post the answers there in just a second. So take your best crack at it, and then we'll see where we go from there. So when you're looking at that sulfur structure, sulfur is in the 6A family, and so it should have 6 electrons around it in total when it goes to do its bonding. And when you're looking at that ring structure there, it contributes 1 electron to each of the bonds that surround it. And so if it has 6 valence electrons total, 2 of them are in those bonds. That means it has 4 electrons that you would still have to draw in there. And so basically, if you're drawing like this Lewis dot structure, what it would look like is that each one of them should have 4 more dots on it. So like here's one in that bond, here's one in that bond, something like that. So it'd have 2 pairs for electrons. Okay. And if anything I'm saying doesn't make sense at all, you guys just jump right in and then let me know, and I'm happy to help out if anything's not making sense. All right. When you're looking at the bond angle then, we have a tetrahedral electron geometry. In other words, when you hear that, it means that the electrons are in 4 different places around each sulfur. You have some on the top, some on the bottom, some on the left, some on the right. So anytime you have a tetrahedral electron geometry, the general angle is that 109.5. That's kind of where it starts, but that tetrahedral electron geometry, that 109.5 answer, is assuming that you have 4 bonds in all directions. So if you were to picture a methane molecule, maybe, think about like if you had C in the middle and 4 H's all around it, it's a bond in all directions. That's where that 109.5 comes from. However, when you've got your those lone pairs, the lone pairs take up a little bit more space than the bonds do. And so it generally goes down about 2.5 degrees-ish per lone pair. So because we've got 2 lone pairs there, it's gonna knock down your bond angle by roughly 5 degrees to about 104.5. The AP exam does give you a little bit of a window of of correct angles there. So really, if you guessed anywhere from like 104 all the way up to that 109.5, anywhere in that range, they would have accepted as a correct answer. Okay, and then electron configuration, since it doesn't specify one or the other, a shortcut way or the long way, you could have written either one of those answers that you guys see there. Any questions so far? Okay. Okay, that's looking better. All right, so now we've got this photoelectron spectrum here. And so just a little reminder of what photoelectron spectroscopy is all about, and just looking at this graph. I know it's been a while since we've looked at one of these, so you can remember what's going on here, right? So you have that relative number of electrons on the y-axis and then binding energy on the x. And what's a little bit weird about the photoelectron spectrums is that the x-axis is labeled so that the largest values are all the way on the left, and then the smallest values are all the way on the right. Usually that's not what it looks like when we look at graphs, right? Usually when x equals 0, that's all the way on the left-hand side, but it's reversed. So what this is supposed to represent is how much energy it takes to take an electron away. You're looking at this binding energy. And so binding energy is going to, sorry, just letting somebody in there. The binding energy is, you're measuring how strongly the electrons are held to the nucleus. So if it would be very, very difficult to take the electron away, then you would have a very high binding energy. So it would be where that peak X is where it would take enormous amounts of energy to try and take that electron away. If it's a little bit easier to take an electron away, then you're looking more at like peak Y. So I'm going to give you guys a second to see, give you guys a few minutes to kind of look through that part D and try and figure out what it's saying. Come up with some kind of answer about Coulombic forces there, and see if you could draw in that peak Y that it's asking you for there. It tells you about how peak Y is for chlorine, and it wants you to draw in a sulfur atom instead. So give you just a few minutes. Just try and do part D only. Okay, part D only. Are you calling me, Jenna? Sorry.
Yeah,
Yeah, sorry.
sorry.
You
I
were
didn't know
muted
if I
there
was
for a
allowed to
second. Yeah.
unmute.
Okay.
I just have a question for the other one.
Yeah.
For like the thing where you know that it's tetrahedral because there's like 4 places where the electrons are.
Yep.
If there's like a double bond or a triple bond, that counts as one place, right? Where the
Yes, it
electrons
does.
are.
Yes.
Like there was a double bond.
You
Okay.
got it. Perfect.
Got it. Okay.
So Jenna was just asking about part B there that you see where it's asking about the bond angle, and we talked about the electron geometry, how the electrons are in 4 places. You've got like a lone pair, 2 lone pairs, and then 2 bonds, and how that affects your bond angle.
Oh, okay. So it's not like we think of it as like an octagon.
Right. That yeah, you're not taking that 360-degree circle and dividing it by in an octagon kind of shape. You got to think about it in terms of the bond angles that you guys were taught. And here's kind of the nice thing, since this is an open note exam, you guys could have, do you remember that shapes sheet that Mrs. Zinger and I gave you guys that has like that summary of all the shapes and the bond angles and all that? That guy's up on Schoology if you have misplaced it. That might be a nice one to have nearby just in case on test day if you want it, right? It's an open note exam, and that one's kind of a nice little quick reference sheet that you could use.
Got it.
All right. Okay, does anybody need more time on D before I go over answers? I don't want to rush you. All right, let me pull up my key here. All right, so let's look at this part D. Okay, so what we're gonna try and figure out here is we're going to do looking at these orbitals. So remember how I said that when you look at the x-axis, how it's bigger all the way on the left. That means that it requires lots of energy to take those electrons away. So if it helps you, you might want to label the peaks on a photoelectron spectrum. They go right along with the electron configuration. So it tells you there in part C, we were trying to find the electron configuration for sulfur, but this photoelectron spectrum is for chlorine, right next to sulfur on the periodic table. So if we did chlorine's electron configuration, it would just end with 3p5 instead of that 3p4. So what I did was labeled the peaks on that photoelectron spectrum, so you could see which ones go with which one, with which orbital, right? And so that X peak there represents the 1s orbital. It would take the most energy to take away those core electrons that are closest to the nucleus, because a couple different reasons there, right? It wants you to identify what orbital that peak X is. So it's the 1s orbital. And then we want to explain why. How did we know that it was 1s based on the stuff that you guys have learned about Coulomb's law? So there's a couple different ways you can kind of tackle this problem. One is that if you're looking at chlorine versus sulfur, and identifying bonding energies between the two atoms that we're going to be comparing here. The chlorine has higher effective nuclear charge than sulfur does. Chlorine has 17 protons, sulfur has 16. In addition to that, chlorine's got a smaller radius than sulfur. As you go from left to right on the periodic table, atomic radii decrease because of that effective nuclear charge. That chlorine, if you think about that Coulomb's law that you guys learned, it's KQQ over R squared. The QQ are your charges, so that's your protons and your electrons, and then your radius, how big the atom is. If you have really strong Coulombic attractions, the atom shrinks down in size because those attractive forces increase. If there's lots of charges, or if the radius is small, because you're dividing by a smaller dividend there, and so your answer there is going to be larger. Right? So if you have higher charges or smaller distances, those result in higher Coulombic forces of attraction and therefore higher bonding energies. So that's how we know that when you're really close to the nucleus, you're going to have that high bonding energy, right? If you look at that next question for peak Y and identifying where peak Y corresponds to some orbital. They just leave that ambiguous so you don't know which one it is. That's the 3p5 electrons for chlorine. But it says, where would sulfur show up on that peak? If you had to draw on sulfur's outermost orbital, it would be a little bit shorter than the chlorine one that you see there, because it would only be representing 4 electrons instead of chlorine's 5. So a little bit shorter. We're looking for relative number of electrons. And chlorine, since it has higher number of protons there, higher effective nuclear charge, it can hang on to its electrons a little bit stronger than sulfur can. And so sulfur's outermost electrons would be a little bit easier to remove. And so we put the peak a little bit further to the right of that peak Y that was drawn in there.
I have a quick question.
Yes, that's a hard question there. So yeah, go ahead.
How does the effective nuclear charge contribute to the level of attraction between the valence electrons and the nucleus?
So if you have a substance that has a higher effective nuclear charge, if you think about like just Coulomb's law in general, I'll write it over here so you guys can see this. It's KQQ over R squared. And so the Q and the Q are your charges. So if you have more protons, more electrons, then your F, forces of attraction, are going to be greater as well. Or if your radius is smaller, when you divide by something small, your answer is big, right? So the fact that that chlorine has 17 protons, 17 electrons versus sulfur only has 16 protons, 16 electrons. There's more attractive forces going on there in the chlorine, making it more difficult to take its electrons away than sulfur's. And that's why so photoelectron spectrum here, spectra that you see here, this is one way this is a way that we can kind of see ionization energies in action. That's one of the reasons that we know that a P cloud is higher in energy than S clouds are, even if they're both in the third energy level, for example. So if you're looking at the 3S versus the 3P, we know that a 3P cloud is a little bit higher in energy than a 3S because of that. When you're looking at those binding energies, you get different peaks for the different types of orbitals. It's not everything that's in energy level 3 is exactly the same, or everything that's in energy level 2 is exactly the same. Right? So if the orbital itself is higher in energy, it would be easier to take the electron away from that higher orbital. You don't have to work as hard.
Got it. That makes sense.
All right. Any questions there with the photoelectron spectrum? Anything at all related to photoelectron spectroscopy that's kind of jumping into your brain after seeing one of these?
This is a different kind of question,
Yeah.
but like, are we gonna have to know like what kind of like is there a similar spectrum where we have to understand like the wavelengths of electrons or particles that are released from an atom?
The only thing I have ever seen where they've asked about wavelength is you guys learned from physics last year, the E equals H times frequency, right? Planck's constant times frequency, or speed of light is frequency times wavelength. If you look at your AP equation sheet, both of those guys are on there. And they give you Planck's constant, they give you the speed of light. They did ask a question a couple years ago for our AP students to use that equation, but it really was super straightforward. It was like, here's the energy, and here's Planck's constant, what's the frequency? It was kind of, here's two variables, solve for the third, the unknown part. So it's technically possible. I would be surprised though if they ask something like that, because just because it's kind of weird, your test is limited, and to have something so small show up on the AP, on a very shortened AP test, it would be strange to me. It's possible, but I just don't see it happening.
Got it.
Okay. All right. So let's see. If we don't have any photoelectron spectrum stuff, then maybe I'll give you a second here. So now we're going to look at a little bit of some kinetics. And so it's going to have you solve for the orders with respect to that sulfur in that equation that it gives you there. So we could have you guys do part E there, parts 1 and 2. And then you can actually also sneak a peek at that part F. See if you could figure out those guys. So I'll give you a few minutes. Try E and F. See what you come up with. And then I'll put my answers up and we'll talk through them in just a few minutes there. Okay. And if you have any questions, anything's coming to mind while you're working, definitely shout out, because that's what we would do if we were in class, right? Just because we're doing it virtually doesn't mean you're not allowed to ask questions. Are you ready?
Yeah.
Yeah? Yeah? Anyone want me to give another minute? We're good? Oh, thanks, Sophia. I see your thumbs up there. Thanks. Okay, so let's look at parts E and F. I'll put my key here. Okay, so what you're looking for, if you do get some kind of kinetics question on Thursday, you're going to be looking for, if it asks you to find the order with respect to a certain chemical, is you want to find 2 trials where just that chemical only changes in concentration. Because when you're looking at kinetics, if you look, if you were asked to find the rate of hydroxide, let's say, and you looked at trials 1 and 2, the sulfur is changing there. Sulfur is the only one that's changing. The hydroxide stays the same. So those trial 1 and 2 are good ones to look at to determine what impact the sulfur has on the rate, because you don't want to have two variables changing at the same time. Otherwise, you don't know if the rate is changing because of the sulfur or because of the hydroxide. So that's why I decided to use trials 2 and 1. Because just sulfur was changing, the hydroxide was staying constant. So any impact um, of the rate changes, it has to be because of the sulfur. What you're going to do is set up a ratio there of one rate for one trial versus the rate of the other. And then what you'll set that equal to is the ratio of the molarities of those two trials raised to some exponent that I just called x. The orders are all exponents, and so we're trying to figure out what that exponent is. And so if you do 2.1 divided by 0.699, that's roughly 3. And then when you divide that 0.3 by 0.1, that's also 3. So if we simplify that equation down, we basically have 3 equals 3 to the x. And so x must be 1. And so we would say that it's a first order reaction with respect to sulfur. If we wanted to know the value of hydroxide that in that data table, that question mark there that it has for the molarity for hydroxide, it's telling us it's first order with respect to hydroxide. So what I did for that guy is let me find 2 trials where just the hydroxide is changing and nothing else. And so I used trials 2 and 3 because the sulfur was being held constant there. And so any changes in the rate are going to be due to the hydroxide only. And now this one, it's a little bit different. We know what the order is because it told us first order with respect to hydroxide. So we know the exponent. We just don't know what the concentration is of that hydroxide in trial number 3. So far, so good. Just turn on that mic and yell at me if I'm going too fast. Good? Okay. All right. For part F, so it's telling us the next day the student comes in to do trial number 4 using the same concentrations as in trial 1, but the reaction occurs much slower. And it shouldn't, right? If once you know what the order is and you know what the concentrations are, it should act the same way. But he notices that the temperature in the lab is lower than it was the day before. So it wants you to come up with some kind of explanation, particle level wise, that would help explain why the rate might be lower in trial number 4. So the couple of things that it's looking for there, if something's at lower temperatures, then that means that particles are moving at a slower speed, right? Temperature is a measure of average kinetic energy. And you guys know from your physics days, kinetic energy is 1/2 mv squared. So if temperature's coming down, the velocity of those particles are coming down. So you would want to say something about them moving slower. That's part 1, but it wanted 2 explanations, not just 1. So yes, the particles themselves are moving slower, which would help explain why the rate would be lower and slower, but that's not the only thing. The other reason would be that because the particles are moving at a slower speed, they are colliding less frequently. And so if the particles have less energy, less collisions, then you're going to have a lower rate overall. Any questions on that kinetic stuff? Doing all right? Okay. Then if everybody's doing pretty good there, how about we sneak a peek at this next guy? So if we take a look at this question, we'll kind of see where you guys are at here. So this question is going to focus on a couple different things: atomic theory, so how are atoms structured; periodicity, so how different properties about the atoms, how they arrange themselves on the periodic table, how we get all those periodic trends. So I'll ask you some stuff about that, and then some bonding related questions. Okay, so we have some data that's provided for us about fluorine, oxygen, and xenon. First, ionization energies. It wants us to write an equation for the ionization of atomic fluorine. So you're writing kind of like a balanced chemical equation for what's going on there for ionization energy. And then we're going to try and figure out why the ionization energy for fluorine would be greater than the ionization energy of oxygen. And then you're going to try and make a prediction of where xenon would fall. Do you think it would have a higher ionization energy, equal to, less than fluorine? So I'm going to give you guys a few minutes. Just try parts A, B, and C, and then you can hang tight. Don't go on to part D just yet. Okay, so a few minutes for A, B, C. So the first thing there, where we've got, we're writing a balanced chemical equation. It's kind of weird. You know, I even had to kind of stop and do a double take when I was doing this question myself, when I was making up my answer key. Because usually we think of fluorine, when fluorine turns into an ion, it turns into fluoride, an anion, right? But it's talking about ionization energy, which is how hard it is to pull an electron away from an atom. So we're not adding an electron onto fluorine, the atom, to turn it into fluoride, the ion. We're taking an electron away from a neutral fluorine atom to turn it into an F plus ion, which is kind of strange. So if you're thinking that's kind of weird, you're right. That is kind of weird. Fluorine doesn't usually give up electrons like that, right? Fluorine's usually taking on electrons, not giving some away. And because of that, you have to put in a pretty substantial amount of energy in order to ionize fluorine. And so you technically don't have to have that 1681 kilojoules in your reaction, but I put it in there just to emphasize that it's like an endothermic thing. You have to put the energy in order to pull that electron off. If all you have was F going to F plus plus an electron, perfect. That would get you credit if this was the real AP exam. Okay. For part B, where it wants you to compare those ionization energies for fluorine and oxygen, and you want to make sure that you talk about both atoms in your response. When you're comparing atoms that are in the same energy level, so fluorine and oxygen are both in the second energy level on our periodic tables, any differences of elements that are in the same energy level are going to be due to their differences in effective nuclear charge. So there's that Coulombic attraction stuff showing up again, that fluorine has 9 protons, 9 electrons, versus oxygen's 8 protons, 8 electrons. So Coulombic attraction wise, fluorine has more Coulombic attractions, and therefore it's harder to pull those electrons away from that atom as a result. And if you're trying to figure out there for part C, when you're comparing xenon is not in the same energy level as our oxygen and fluorine. It's way down there on the periodic table in row 5. And if we think back to that Coulomb's law equation one more time, that yes, xenon has a heck of a lot more it has a heck of a lot more protons and electrons. However, those electrons that you're adding are way out there in the 5th energy level. And so the radius is much, much greater in our xenon atom. And so the forces of attraction would be much, much less, because you're taking that really big radius and then squaring it on top of that. So the forces of attraction come way down. And so it'd be much easier to remove xenon's valence electrons than it would for fluorine. Okay. Doing okay? Any questions on A, B, C? Okay. Then what I'm going to do for this guy, I'm just going to show you part D, the answer there for part D. On your AP exam, they have told us that you guys are not going to have to do any drawing. So no particle sketches, no Lewis dot structures. They said that all that stuff is kind of off the table. They're not going to do that because some people might choose to type their answers. And how would you type a Lewis dot structure, right? That's like impossible. So you won't have to draw anything. What you might have to do though, something you might be asked to do is to look at Lewis dot structures and see if they are valid. Which one might be the best Lewis dot structure based on formal charge. And so you can compare certain structures. So they won't have you draw them, but they might have you analyze them. Okay. Any questions on that? Just that general no drawing kind of stuff?
Could we go over the way to analyze different structures based on formal charge?
Yes. So there was a little funny equation that I gave you guys for formal charge. It was to determine the formal charge of an atom. You might remember me giving you this funny little phrase, very bad day. And the very bad day, V stood for valence. So you would look at how many valence electrons the substance has based on what column it comes from on the periodic table. The B in very bad day actually stands for bonding electrons. So how many electrons are trapped in a bond? And then D, oh my gosh, I'm blanking out myself. Very bad day. What does the D stand for? Holy cow. See?
Dots.
Thank you. Oh my goodness. Yes. Who was that? Thank you. Was that Jenna? Somebody? Thank you. Thank you. Dots, right?
No, that was me.
Thank you. Okay. Oh, my brain is on May mode as well. Okay. So it stood for dots. So how many dots are on your substance right now? So if we looked at like this oxygen atom right here, right? And we said, what's the formal charge on that oxygen atom? Oxygen has 6 valence electrons. One of the electrons is in a bond, and then it has 6 dots surrounding it. So it would have a formal charge of -1. When you're trying to decide if your structure is the best one formal charge-wise, what you're going to be looking for is that your negative formal charges are show up on elements with high electronegativity values. You also want to make sure that your things usually don't have a positive formal charge. If you have a positive formal charge, it basically means it's giving away more than it's getting back. And so as a result, it's kind of not a win for that particular substance, that it's helping somebody else too much. So when you're looking at those formal charges, you calculate it per atom, and you would look and see if you did have any formal charges, if they gave you 2 different structures to compare, and you were deciding, is this one better, is this one better? If you saw any positive formal charges, you'd be like, nope, that one's out, right? If you looked for, if the negative formal charges ended up on things that have lower electronegativities, that's probably not going to happen either, because electronegativity means that it can attract electrons very well in a bond, and it's probably not going to give that away, right? And so those are the couple of things that you'd be looking for. So no positive formal charges if you can avoid them, and you want those negative formal charges on the things with high electronegativities. Okay. Good there. Okay, so I just gave you guys the two structures that it's asking about there. So you can see what the XeO3, you would have just that lone pair of dots on the Xe. And then for the XeF4, you'd have your 4 Fs bonded, and there's an expanded octet. Does anybody remember when you're allowed to do expanded octets? Anyone want to jump in?
For sulfur, for phosphorus, and for noble gases.
Yeah, phosphorus and sulfur are the two common ones. You'll see it a lot. You have to be in energy level 3 or greater on the periodic table. So at least 3 energy levels for your atom in order to do those expanded octets. The reason why you need at least 3 energy levels is because the expanded octet stuff, why it has that ability to put more electrons around, it comes from unoccupied orbitals that are in the unoccupied d orbitals. So when you guys think of your electron configurations, if you're in the first energy level, it's just 1s2. If you're in the second energy level, you could have 2s2, 2p6, there's just s's and p's. In the third energy level, we have 3s2, 3p6, and then those 3 Ds, they don't show up until after the 4s2s. But they're there, they're just unoccupied, waiting, but there's space available, it just hasn't been filled in yet. And so those, you have to be at least in the third energy level or greater to get those expanded octet things. If you're in the second energy level, there are no d orbitals for those extra electrons to spill over into, and so there would not be an expanded octet possibility. Okay. So knowing that that's what those two structures should look like, because you guys will not be asked to draw, you might be asked to analyze, but not draw. Take a look at those two structures there, and I'm going to have you guys go on and look at parts E and F. So if I kind of scroll ahead here. So you know what the two structures are supposed to look like. So now take a look at some shapes, hybridization, and then polarity of those molecules. So I'm going to give you a few minutes to try parts E and F. And I'll pull up that structure here on your screen one more time. Okay, so you could look at those two guys there and try to figure out shapes, hybridization, and polarity of some of those things.
Mrs. Carlson,
Yes.
when it's asking for the geometric shape, does it want like the like electron pair shape, or like the one like that takes into consideration like which ones are bonded and not?
Awesome question. So if it wants just the geometric shape, it's looking for the molecular shape. If it wants the electron geometry, it'll specifically call out electron geometry.
Okay.
So it's looking for molecular. So I have some notes here. If you did just kind of jump in a little bit and you weren't here for the whole time, we did talk about how you might want to have that sheet that Mrs. Zinger and I gave for you guys about bonds and shapes. You might want to have that guy printed and nearby on test day. Since it is an open note test, it's totally legal to have it out on your desk. And then it's one less thing for your brain to have to cram and memorize. It might help you that way. So I think it was Cassie, I'm just trying to base on voices, that was asking about the electron geometry versus molecular geometry there. That when you look at that XeO3 molecule, so we're looking at that one on the left, so we've got the xenon with the lone pair on the top and then bonded to 3 oxygens. It has tetrahedral electron geometry. The electrons are in 4 places, 1 to each O, and then the lone pair at the top. Now, tetrahedral electron geometry can turn into a few different molecular shapes. based on if all 4 of those locations where the electrons are bonds, or if there's any sets of lone pairs. So whenever you have, if you had 4 bonds, then the shape of the molecule would also be tetrahedral. But if we're going to replace one of those bonds with a lone pair of electrons instead, it turns into a trigonal planar. Trigonal because you've got 3 bonds, right? Tri for trigonal pyramidal. And then that one lone pair causes those 3 bonds to kind of come down at an angle. So they're not flat, those 3 oxygens, but they kind of make a little bit of a pyramid shape. The hybridization of those xenon electrons are sp3, that the electrons are in 4 places, the lone pair, and in each of those oxygen directions, right? This isn't technically how it officially goes, but it might be easy, a little trick to help you remember. If the electrons are in 4 places, you have like an S, a P, and another P. Is an easy way to remember that. If your electrons were in 3 places, so you had a trigonal planar shape, looks something like that, right? Then this isn't officially how it goes, but it just might help you to remember, let's call that direction S, this one P, and that one P. So it would be sp2 hybridization. If you had a linear structure of some kind, and it asked you about the hybridization between those guys, you could have sp, right? So if electrons are in 4 places, tetrahedral electron geometry, it's sp3 hybridization. If your electrons are in 3 places, so you have some kind of trigonal electron geometry going on there, it would be sp2 hybridization. And then if the electrons are in 2 places, sp. Any hybridization stuff you want to ask while we're talking hybridization? Okay. And then that electron geometry of the XEF4. So here's that XEF4. So there's that expanded octet. So fluorines all around. And then those fluorines, if you want to think about it, are all on a flat plane. And the lone pairs on that xenon are above and below that flat plane. And so it would be a square planar molecular geometry. It's octahedral electron geometry. The electrons are in 6 places, the 4 bonds and the 2 lone pairs. You might remember when we did our shapes lab that that depending on, for those expanded octet stuff, if you had octahedral electron geometry or trigonal bipyramidal electron geometry, and you started to remove, when we did those shapes labs, it's like, which one comes off first? Do I take off the axial things, the ones that are up and down, or the equatorial things, the things that are like around? Think of like the equator on the planet Earth, right? So if you have octahedral electron geometry, where the electrons are in 6 places, they're going to remove the axial electrons first. The top and bottom ones are where lone pairs would go if you have a choice of where to put those lone pairs, right? And so that's why in the XEF4, the 4 Fs are going to go on those 4 equatorial places. So you have that equatorial, here's another equatorial, right? That's where those 4 Fs are going to go. And then the lone pairs go in the axial positions. So that's when I say it gets removed first. That's where if you had a choice of where to replace a bond and put a lone pair instead. That's where they go in the axial positions first for those octahedral ones. And then I'll just scroll a little bit down here. The opposite is true if you have trigonal bipyramidal electron geometry. That in that case, electrons are in 5 places. So you have the up and down axial, and then you have the 3 on the equator, kind of like in a peace sign shape. They're going to remove the equatorial ones first that time. Okay. So might be handy to have that sheet nearby, then you don't have to worry, right? And it's just right there. You can look it up. For the polarity part, if you had to guess whether XeO3 is going to be polar or nonpolar, the lone pairs on that XeO3 cause an uneven distribution of charge on that molecule. Lone pairs take up more space than bonding electrons do. In fact, all trigonopyramidal molecules are going to be polar because they'll have that lone pair there that pushes those other atoms down into that pyramid shape. You guys know from your physics days when we were talking about how you could have a bond that's polar, but the molecule might be nonpolar, as long as the bond dipoles cancel. But if you're thinking like, what is she talking about? If I drew carbon dioxide is the most common example of that. If you look up the electronegativity difference of carbon versus oxygen, it falls into a polar range. Electrons are more attracted to the oxygen than they are the carbon. So you have a general bond dipole that this oxygen pulls to the right and this oxygen pulls to the left, but the carbon dioxide molecule is linear overall. And so those bond dipoles cancel out and make it a nonpolar molecule overall. When you have something like that XeO3, where you have the lone pair on the Xe, it forces the other oxygens down at kind of these weird, funny angles. And then it's difficult, in fact, impossible, for these bond dipoles to cancel out. If you think about your physics days, right? Those 3 vectors would not neutralize one another there. Okay. Questions on that guy at all? Doing okay? Ready for another one? Who's excited? Getting burnt out yet? Okay, stretch it out, stretch it out. We're about halfway through-ish, right? Okay. All right, we could do this, right? This is more than twice the length of your test. Think about it that way. That's pretty good, right? Yeah, it'll be like your test will feel like short compared to this stuff. Okay.
I have a question, Mrs.
Yeah,
Carlson.
what's up?
Is there gonna be like an experimental design question?
Well, that's an awesome question. I have no idea what they're going to throw at you, but it wouldn't shock me to have some kind of experimental design because it is an easy thing to type, and you're actually going to see some kind of experimental design thing in the very next question. Oh, it's like I planned it. I was like, let me find a question that has something like that in there just so you get a little bit of practice with it in case you see one like this on test day, right? Okay, so let's take a look at this next question here. So this guy is going to cover 3 different topics. So we're going to have some stuff about intermolecular forces, some stuff about thermo, and the lab setup, something like you were asking about there. This is just my opinion. This is not official from the College Board at all, but I'm betting you guys are going to have some kind of question about intermolecular forces on there, because it was supposed to be the heaviest covered topic on the exam anyway, and it's still on the list of allowed topics to be tested on. And it's something that they could easily write an essay question for, and since they're not having you draw stuff, they might, and you could type your answers. It's very easy to do a short answer kind of stuff on intermolecular forces. So it's my prediction. I don't know anything official, but it is my prediction that you'll have something about intermolecular forces on there. So I would really make sure you study up on those. Okay.
Are they all going to be written then, or like typed question, like answers? Will it be like no math? Like how will you show math if
So that's a really good
like
question.
typing?
Yeah, so you can type, but you don't have to type. They said there is, if you look at that Google Doc that I shared with you guys, the latest and greatest of all the information I know about the AP test, it does have on there like a typing checklist or something. I don't want to get like, if you're trying to type a chemistry answer. This is just, again, my opinion. You have to do what works for you on Thursday. I think you guys are more comfortable writing your chemistry than you would be typing your chemistry. If you do choose to type, they are making some allowances. So if you were like writing H2O, they don't care. The 2 doesn't have to be subscripted in little. It can just all be, regular text. But they might throw math problems at you. And to try and type the math, I think you'll find that more stressful than writing and taking a picture. So again, it's entirely up to you. Please practice with that upload submission website that's up there. So that way, the flow, and make sure, like if you have a newer iPhone, that you have the right format of your pictures that the College Board website will accept and all that. Please, if you haven't already done that practice thing, please go there and do it 1, 2, 3, 4 times until you feel like, I know how to do this. This is totally fine. So you feel comfortable with it. Okay. Because you want AP testing stressful enough. You don't want to have to stress about typing it correctly and uploading it correctly, and this isn't formatted correctly and all that. It'll stress you out too much. So just practice. Okay.
I found this one website. I know that College Board is allowing people to type like certain symbols, like if you're on like a Mac. If you press like the option button or like the alt button and then press like any key on the keyboard, there's a bunch of different symbols that you could use. So if you need to type in any symbols, or if you're on a Windows, you can just go to this website, which is what I did.
Awesome.
You can type any symbol that you need.
Thank you for sharing. Keep in mind, guys, the people who grade these AP tests, they're AP chemistry teachers. All of them are AP chemistry teachers. They all have students who are in the same boat as you guys, and they are just as worried about their students as we are about you. And they all are rooting for you. This Facebook group that I'm on with AP chemistry teachers, they say that if we can, like, they find you points. They will, like, that, if that's solid chemistry, it doesn't match what the answer key says you're supposed to write down. But if you have logic and reason and it makes sense, they give you the credit. And so these are real people. They want you to do well, and they understand the incredibly weird situation that you guys are all in. And so I think they will look the other way a little bit if we have weird typos and things like that. But it's just a crazy situation this year. It's just nuts. Whew. Okay. So that being said, let's take a look at this question. Let's see what this guy's all about. Okay. So we have this compound urea. It gives us the Lewis dot structure. So like I said, they might provide you with Lewis dot structures and ask you to analyze them in some way. So it wants to know about some hybridization that's going to occur on that carbon atom. It wants you to think about hydrogen bonding. So there wouldn't be, if this was your test, it's not going to have you actually draw it, but it might ask you to describe where you would draw it. So it's like, I would draw a line between here and here, something like that, right? So I'll have you look at A and B, and you guys do that A and B. And we'll put answers up in just a second. Those should go relatively quick, those 2 parts. Shouldn't be too long. We should have on that hybridization of the carbon atom, the electrons are in 3 places around the carbon, to the left, to the right, and up towards the oxygen. And so we would have sp2 hybridization around that carbon atom. The double bond there counts as one location. Okay. And then there's a couple different options of where you could have drawn your dashed lines there to represent your hydrogen bonds between the water and the urea. So just a couple of reminders of the requirements to have something for hydrogen bonding. Like, how do you know if something's going to hydrogen bond to something else? So you're going to look, here's the 2 requirements that need to be met. You look at molecule number 1, and you'd say, does this molecule have a hydrogen that's bonded to fluorine, oxygen, or nitrogen? If it does, it could hydrogen bond with another molecule nearby, as long as that molecule has lone pairs on fluorine, oxygen, or nitrogen. That the hydrogen from molecule number 1 is attracted to those lone pair electrons on molecule number 2. And it's a really strong intermolecular force, those hydrogen bonds really strongly hold molecules together. Okay, so your description of where you would have your lines there, it could be from the hydrogens on the water molecules to the oxygen on the urea. You could have that attraction. You could have the hydrogens from the water molecules be attracted to the lone pairs on the nitrogen of the urea. You could also have some lone pairs. What else am I missing there? Right, the oxygen from the water molecule could be attracted to the hydrogens on the urea, is the other kind you might have there. So there's lots of different options. As long as it meets these 2 requirements, you're good. Any hydrogen bonding questions that you might have? Okay, so let's take a peek at this next page then. Part C is a little bit of math, and we're going to figure out the concentration of a saturated solution. And then we have some Le Chatelier in part D. And then here's that little bit of design that Pranav was asking about in part E. So I wanted to throw one of those at you. So I'm going to give you guys a few minutes. I'd like you to try C, D, and E. And I'll check up on you in a couple minutes. We'll see how you're doing. If you want to find the concentration of that urea in moles per liter, you know how many grams they dissolved in 5 milliliters. So we're basically taking that density and converting it to a molarity using the molar mass of urea that they give you up there in the problem. So I just said, okay, I took that 5.39 grams, we dissolved it in 5 milliliters, a little bit of factor label there, and we're able to figure out the molarity of our saturated solution at 20 degrees. So that's kind of a key thing here, that's the saturation point at 20 degrees. When you look at part D, it tells you that at 25 degrees, the saturated solution, the molarity goes up. So we're trying to figure out here, when we're dissolving that urea and we are changing from, see, if you look at the top of the screen there, it's solid on the left, aqueous solution on the right. And so we want to know, is it, as written that way, is it endothermic or is it exothermic based on this new information? So it's telling us that basically when we heat it, when we go from 20 degrees Celsius to 25 degrees Celsius, that the molarity of that aqueous stuff increases. So when we heat it, it's shifting this way towards the aqueous ions because the molarity in part D is higher than the molarity in part C. So we're making more ions, more dissolves upon heating. When we go from 20 to 25 degrees, it goes to the right. So if that's the case, that must mean that the heat energy is over here on the reactant side, because when we heat it, it shifts right. And if the heat energy is on the left-hand side, that makes it an endothermic reaction. Any questions so far? Okay. And then for that part E, where it told you you could see all the pictures of the supplies that you have available to you. And what we're trying to figure out is the molar heat of solution for urea. So molar heat of solution, what it's basically asking you to solve for is this part right here, right? How much heat is released when you dissolve a mole's worth of urea in water? What's the Q per mole is what we're trying to solve for there. And so when you look at the supplies that you're given, you've got your urea, a cup, you've got some water, a balance, thermometer, all that kind of stuff. So if you want to know the heat of solution, how much energy is being released by that urea upon dissolving, actually I should say it's endothermic, how much energy would be absorbed by your urea as it dissolves there, that you would need a few different things. We know that energy is always conserved, so the heat lost by the urea is going to be the heat gained by the water. You might remember doing this Q equals negative Q kind of situation, that whatever heat transfer takes place, if urea is absorbing something, it's equal to whatever the water lost, vice versa, right? So if we could monitor what's going on with our water, you could get the mass of that water that you're putting in the cup. So we need this guy. You can do an MC delta T problem. And if you know the mass of the water that you put in that cup, depending on how you do it, you might need the mass of the cup itself. Unless you tear it and tell it to ignore the cup, then you wouldn't need the mass of the cup itself. But you definitely need the mass of the water. So that would be this variable. It tells you in the problem, you know the C value for the solution once you put the urea in. So you know that this C value right here is 4.184. You could use the thermometer that you are provided with to find the initial temperature of the water and the final temperature of the solution once you've put the urea in and you dissolve it. So we would definitely need both of those numbers in order to get all the variables on this side of our equation. Once we know that answer on the right-hand side, that's how much heat our urea is absorbing while it's dissolving. So we know the Q, but we don't want to just know the Q. We're looking for the molar heat of the solution. So we need to know how many moles of urea are dissolving. So that's why we also need this mass of urea that we could convert into moles using the molar mass. So then we know both the Q and we know the moles, and we could divide those guys to get our molar heat of solution. Questions on that last one? That one's a little trickier, where you gotta think of all the different pieces you need there, designing your experiment. Okay. Let's see. Should we push through one more? One more? You want to do it? Yes, bring it on. Okay. All right. Here, we'll make this our grand finale tonight. We got about 20-ish minutes left together. Okay. So let's take a peek at this question and see what we're going to try and tackle this time. So this one's going to have some stuff about atomic theory and periodicity. So either stuff about the atoms themselves or periodic trends kind of stuff, how it's arranged on the periodic table. We're going to have some intermolecular forces stuff, how the molecules interact with one another. And then we'll also throw some thermo in this guy as well. Okay. So let's kind of read through our question and see where we're going. So this first guy is asking us about the halogen family there, and we want to know which one would have the longest bond length, and we're going to try and explain why it would have the longest bond length. And then, no, that wasn't an accident. It goes from part A to part C. I intentionally chopped part B from this question because it had some stuff on the exam that you guys won't see. This guy's asking about boiling points. Try to explain differences in boiling points. So I'll have you look at just those two, A and C. See what you come up with, and we'll do answers in a minute. For which one would have the longest bond length, it's going to be the iodine molecule. You have to think about the structure of the iodine atom and the fluorine atom, chlorine, bromine. Iodine has 5 energy levels, so its valence electrons, where all that bonding occurs, are going to be the farthest away, leading to the longest bond length. That one's pretty straightforward, I think. Not really a surprise there. For part C, where it's talking about the boiling points, so bromines is 332, where that BrCl is 278. So we want to look at intermolecular forces and try to explain what's going on. So if you look at bromine, bromine is a non-polar molecule. You have bromine bonded to itself. It doesn't get any more non-polar than that, right? And an electronegativity difference of 0. And so if you think about the Lewis dot structure of that Br2 in your head, right? Bromine bonded to itself. And so there is not, the electrons do not head in any one direction. They're just split right down the middle, non-polar. And so non-polar molecules, the only intermolecular forces that they experience are London dispersion forces. It is okay to abbreviate that as LDF. That's an acceptable abbreviation there on the AP exam. They'll know what you're talking about. London dispersion forces are temporary uneven distribution of charge. So these electrons are they're constantly zipping around each atom, right? They're not locked in place like how we draw them in a Lewis dot structure, but all over the place. And so what might happen is that maybe one of these electrons, let's say, zips over, let me switch colors, right? Maybe it zips over to this side of the molecule. Well, then if it gets near another electron that's on this side, it causes that one to kind of shift over to avoid that electron. And so if you are on the right-hand side of this molecule, you get a temporary negative buildup of charge on this side from the electrons that kind of shift to get away from the electron on the other side. That's what London dispersion forces are all about, just temporary, because as soon as this electron leaves and goes on to the other side of the molecule, well, then there's no need for these guys to be all built up over here on this side either, right? So all molecules experience London dispersion forces based on that, just the electron zipping around the atom. It's just for nonpolar molecules, that's all they've got is London dispersion forces. Our BrCl has a combination of dipole and London dispersion forces. So everybody's got London dispersion forces, but BrCl, you're going to have some kind of uneven distribution of charge, because if you were to look up the electronegativity values there, chlorine and bromine's electronegativity is not exactly the same. And as a result, the electrons are going to build up probably a little bit closer to the chlorine than they are the bromine, making this side a little bit negative, this side a little bit positive, just due to their differences in electronegativity. So dipole-dipole, generally speaking, is a stronger intermolecular force than London dispersion forces are. Generally speaking, polar things have higher boiling points as a result because they have those stronger intermolecular forces. However, in this problem, they give us data that says the exact opposite of that. Tells us that the Br2 has a higher boiling point than the BrCl, which usually wouldn't be expected. But we have to explain why that is, because it's unexpected. Usually polar stuff has the higher boiling point. So what's going on here? The reason why it's possible for that generally polar stuff has stronger IMFs than nonpolar stuff, why we could turn that on our head, is the idea of polarizability, which is all about that bromine has more electrons, the Br2, than the BrCl does. And as a result, we end up getting more of that temporary buildup of charge. You get more LDFs are possible when you have lots of electrons. And that concept is called polarizability. So if it does not give you any data, and it just said, predict for me which substance has a higher boiling point, Br2 or BrCl, and it has no data, it just gives you the structure of the molecules only, I would predict BrCl would have the higher boiling point because it's polar, where the Br2 is nonpolar. However, it gives us data that says the opposite. That's when you'll rely on that polarizability piece. If there's like, wait, this doesn't jive, it doesn't work with what I would usually predict to be true. Doing okay there? Okay. Let's take a look at where this guy's gonna take us here for our grand finale. Okay, so looks like we've got an equilibrium going on. We've got an equilibrium reaction. It tells us the delta H, the heat of reaction for that guy. We know how many moles of BrCl are being put into a flask. We know that flask's volume and its temperature. So if D is asking us to calculate its pressure, if that's what we're looking for in this problem, and we have some moles, we have a volume, we have a temperature. That's looking like a PV equals nRT to me, right? And so we want to know before equilibrium is established. So you don't have to worry about the bromine and chlorine forming. We're just looking when we first put the BrCl into the flask, what would that be? So I'll give you guys a second to solve that guy. Let me set that guy up. And then we'll do our last page. Show my answer there. That's a PV equals nRT. We're looking for that pressure. We know N. R would come off of your AP equation sheet. It gives you the value for R. We know a temperature, we know a volume, so it's just a little bit of algebra there where we could solve for that pressure. Right? You could have also solved for the pressure in millimeters of mercury because it didn't specify, right? It didn't say, so you could have used the R value 62.4 as your R and solved for the pressure in millimeters of mercury. That's also okay. All right, last page. Let's see where last page is going to take us. So we're going to write an equilibrium expression. We're going to figure out what the value of that equilibrium constant is based on this information that it gives us here. So you know that 42% of the original is going to decompose. So you're going to use that information to help you solve for a KEQ value. So I'll let you guys do E and F. And we'll put the answers up for those guys in just a few minutes. Try E and F. So here's your E and F. So your equilibrium expression, we always do products over reactants. And remember that your coefficients in your balanced chemical equation turn into exponents when you're writing your equilibrium expressions. So if we want to know the value of that KEQ, we're going to set up an ice table. In order to set up an ice table, we need the initial molarities of that BrCl. Since we put 0.1 moles into a 2-liter flask, the molarity of that BrCl in the beginning was 0.050, this guy, right? And then 42% of that decomposed. So if we do 42% of that 0.05, that means that 0.021 has turned into our products. So then we can use those numbers, plug them into our ice table, that we know the original molarity of the BrCl. This is 42% of that number is how much is leaving, which means we have 0.029 left of that BrCl. On our product side, we always start with 0 products unless they tell you otherwise. And in this problem, because there's a 2 in our balanced equation in front of the BrCl, that change number, the 0.021, is going to be twice as big as the change numbers for the bromine or the chlorine. So I have to cut that 0.021 in half to get the changes that would take place for our bromine and chlorine. Then we can plug those guys in, get our equilibrium expression, and find a value of 0.131. That this is an reactants favored reaction. The reverse reactions favored. It stays mostly as BrCl. Doesn't turn into a ton of product. Any questions on E or F? Okay, grand finale then, grand finale. Let's see, what's G all about? We've got some bond energies here. So it tells us what bromines and chlorines bond energies are. We also know the delta H for the whole reaction. It told us up above that that was 1.6 kilojoules per mole of reaction. And we want to know what the bond energy of the BrCl is. So I'll give you guys a few minutes. I'll have you solve for that. So for that bond association equation, just a little reminder, the bond association energy equation is backwards from what we usually do. Don't we almost always do like products minus reactants, final minus initial, right? The bond dissociation energy equation is backwards from what you're used to because you're going to take the energy of the reactants minus the products. It's a little strange in that way. So you do the sum of the bond dissociation energy of the reactants minus the sum of the products there. So our reactants, we are breaking 2 moles worth of the BrCl bond because of the 2 in our balanced equation when we're solving for its bond dissociation energy. And then we have 1 mole's worth of bromine, 1 mole's worth of chlorine. So the moles part will end up canceling out. You'll just have kilojoules left there. A little bit of simplifying with your math. And per mole of BrCl, it would require 219 kilojoules to break those BrCl bonds. Keep in mind a common question they like to throw at you, breaking bonds and forming bonds. If you break bonds, breaking bonds is always 100% of the time an endothermic process. You have to put energy in to break a bond, You have to put energy in to break an intermolecular force. Anytime you're breaking things, picture like a pencil that you're cracking it, you're breaking it. And so you have to supply the energy to break that attraction in some way. And so that's why our bond dissociation energies are always positive numbers, because you have to put energy in. Anytime you form bonds or you form new IMFs, that's always an exothermic process. It always releases energy. And then when we want to look at if a process overall is endothermic or exothermic, that's where we have that comparison of reactants versus products to see, are we putting in more energy to break what's already there, or are we releasing more energy by whatever we've produced? Okay. Questions?
Why is it backwards?
In order to make the signage turn out properly, it's why it's backwards from what you're used to looking at. Because if you're looking bond dissociation energy, it's how much energy you have to put in to break the bond, right? Bond dissociation energy. And when you're making products, you're actually forming bonds, not breaking bonds, right? And so you have to subtract the ones that you're forming because you're not actually dissociating, you're actually bringing them together. So you have to flip the sign on the bond dissociation energy to get the proper value there, because you're not actually dissociating on the product side. You're actually forming, right? So it's bond forming energy, so you have to subtract instead. Okay. All right.